By now we kinda know how to create objects of custom types and that they get created and destroyed just like any other variable. But there is more to it. So today we'll look under the hood and tap into the machinery that allows modern C++ to be what it is, a flexible, efficient and memory-safe language without the use of any sort of garbage collection. We're talking about the machinery of constructors and destructors. Oh, and we'll also see how it enables us to create objects in a more expressive way. For example, we can create the cat class directly with its number of lives and happiness. Under the hood, when a new object of any custom type is created, a special member function called a constructor is called. New terminology might be a bit scary, but there is nothing complicated about it. It looks and behaves just as a function with just two differences. Its name must match the name of the class or struct exactly, and it does not return anything. Its job is to initialize a newly created object. Other than that, we're free to do whatever we want. There can be as many constructors as we want to have, and each can take as many parameters as we like. Oh, and the constructor might also have no parameters at all. Such a constructor without parameters is called a default constructor. And we can use the equals default after the constructor to tell the compiler that it can generate it as it wants, which is even better because the compiler is usually smarter than us. Note that when such a default constructor is called, it will leave the data uninitialized, unless these data are initialized in place. So if we have a class foo and it has two members, one uninitialized and one initialized, only the second one will actually have a value and the other one will stay in undefined state. To avoid mistakes, we should always initialize data in place unless there is a good performance-related reasons for not doing so. Also note that if we provide no constructors at all, the compiler will generate a default one automatically. Anyway, let's get our hands dirty and write a couple of constructors that take, say, happiness and number of lives values for some cat class. We can see that now we're able to create a cat object providing either just its happiness or the number of lives and happiness together. There is quite a bit of new syntax here, so let's have a more precise look at all of it. The parts after the colon symbol in these two places are called the member initializer lists. Everything that happens in the member initializer list is guaranteed to happen before we enter the constructor function scope. These are actually very aptly named. They really are just lists of values that initialize member variables. The emphasis here is on initialize, meaning that the member initializer list brings the object member variables into existence, and they don't exist before this operation. There is no copying involved. It is important to understand here that the order of operations in the member initializer list will follow the order in which the data appears in the class declaration, not the order in which the variables show up in the member initializer list itself. So the number of lives will always be initialized before happiness. Try to always have the variables appear in the right order in the member initializer list, otherwise it gets quite confusing. If we are afraid to make such a mistake, we can always use the -w all flag when compiling our code to enable the compiler checking this and warning us if we mistype. In the cat example, we see a couple of places where the variables are initialized, so it is important to understand which initialization takes precedence when. The rule is quite simple. The initializer list takes precedence over the in-place initialization. If an initializer list misses a value for a certain class member variable, only then this class member gets initialized from its in-place initialization. And if that in-place initialization is missing, it will remain uninitialized. We can of course do more things inside of the scope of the constructor, but it is a good practice to initialize as much as we can in the member initializer lists and try to leave the rest empty. The reason for this is that in the body of the constructor all the member variables will already have been constructed, meaning that if we now set a value to them, we will perform a copy but not an initialization. After creating our custom constructors, if we try creating the cat object without parameters, we get an error. The compiler sees no default constructor, which would be called in such a case. Seems pretty logical. We did not provide a default constructor at all. However, the strange thing here is if we just comment out our custom constructors for the cat class, it suddenly starts working again. So what's going on? The reason behind this is that the compiler can generate some constructors automatically, under certain conditions. In this particular case, it only generates the default constructor if no other constructors are provided by the user. However, we can easily add this constructor back by adding just one line to our class. The cat constructor equals default. It is important to note here that we are just scratching the surface here, and the compiler actually generates quite a number of special constructors and other useful functions for a class automatically, under certain conditions again. This is a bigger topic, so we will talk about it later in the course, so stay tuned for that. Coming back to our example, there is just one more thing that we didn't cover yet, the word explicit. Google style suggests that if we write a single argument constructor, we should mark it as explicit. But why? Well, without it, there are some implicit conversions that a compiler might perform that are a bit confusing and should be avoided. Let me illustrate this by removing the explicit from our previous cat class implementation and trying to compile the following code, replacing our previous main function with the following. This code doesn't look like it should compile, does it? We are passing an integer into a function where a cat object is expected. And yet it does. So what happens here? Well, our cat class has a constructor that takes a single integer as a parameter. The compiler is allowed to perform an implicit creation and decides that the best way to compile this code is to generate a temporary cat object from the provided integer 42 and pass it into the function foo. Now, if we add the explicit back, the code won't compile anymore. So explicit basically forbids creating the objects implicitly. At this point, it should be pretty clear how the life of every object starts. It always starts with one or another constructor, which takes care of initializing the object's variables, acquiring any resources needed for it, and honestly, there is really not that much more to it. So I guess it is about time we talked about what happens when an object is destroyed. Just as how the life of an object starts with a constructor, it ends with another special function, a destructor. The last thing that happens before the object is completely destroyed, its destructor is called. There are again some rules for how destructors are named and how they behave. There can only be a single destructor for a class, the name of a destructor for a class foo must be tilde foo, and the destructor takes no input arguments and returns no value. A destructor is a good place to release any resources that were acquired during object construction. And just as with the default constructor, a default destructor is generated by the compiler automatically under certain conditions. This is usually how we want it. Compilers know how to allocate and destroy any normal variable that we did not allocate manually. More on that later. So in most cases there is no need for us to write our own destructor. This is the reason why you don't see one in the cat class from before. Nowadays in modern C++, we need to write our own destructor only rarely, mostly when we're implementing really low-level stuff, but it is really important to still know what a destructor is and that they exist at all. There will be more to them once we start talking about value semantics or polymorphism, so stay tuned for those topics, but we'll leave it at that here. So, to summarize today's video, it is important to remember that essentially every object is created by calling one and only one of its constructors, used for a while, and eventually its destructor will be called as the last thing before the object is destroyed. A small exercise for you. To make sure this is clear, try adding some cout statements to the constructors and the destructors of our cat class and see that they get printed. The reason for such a design is quite simple: to ensure control over the resources that each object owns. The paradigm that this design enables is usually referred to as RAI, resource acquisition is initialization. And it is a very important paradigm in modern C++, even though an acronym for it could be better. This means that all resources that a class owns should be acquired upon object creation and released upon object destruction. Well, technically, they also can be transferred to some other object through the mechanism of move semantics, but we're going to talk about this, well, actually in the next video. For now, with the understanding of an object lifecycle, we've made our first steps onto the path of understanding proper value semantics, which is the cornerstone of modern C++ design. Thanks for watching, and if you like this type of content, then do like this video, and if you want to see more, then feel free to watch another video on my channel over there. Thank you and bye.